the top. Okay, so consecutive angles. If you have a parallelogram, all right, I'm just going to kind of highlight on this just a little bit here. So that same thing we were talking about with the question from the homework with the trapezoid. If you have parallel lines, the angles, I'm going to mark angle A here and angle B. The angles on the same side of that, like that side there, in between those two parallel lines, those are called same side interior angles. They're going to add up to 180. So I'm going to write over here, I'm going to say angle A plus angle B has to add up to 180. They're supplementary. So consecutive angles means angles that are right next to each other as you go in order. So like angle A and angle B, I touch them right in order. They're right next to each other. Those are consecutive angles. Okay, now I can make the same argument for different parts of this diagram because the top and bottom are parallel and the left and right are parallel. If I use these two, or sorry, what am I doing here? If I use these two lines as my parallel lines and the top as my transversal, let me grab a different, here, you know what, let me just redraw it here. I'm just going to come over here and sketch this. Alright, so same argument, but if I use these two as my parallel lines and let's say this is my transversal, this angle here and this angle here would be considered consecutive angles. They would also be same side interior. If I kind of turn my paper a little bit, which I do sometimes, like these two lines are parallel, they're on the same side of that transversal, so those also have to add up to 180. So like same argument where we've got angle B and angle C, those would add up to 180 in that diagram. So consecutive angles are what we call supplementary, means they add up to 180. Alright, so I wrote that for a couple more. You can write that for a couple more in that diagram as well. You could say angle C and angle D, that's another set of consecutive angles. Those would add up to 180. And I can also make that argument angle A and angle D, all in that diagram, they add up to 180. Now, how does that help us if we're doing a problem? If you know you have a parallelogram, which is what we're going to do in example 1 here, if you know you have a parallelogram, the angles as you go here, as you go around, they're going to be supplementary to each other. So if this is 140, can anybody tell me what angle 1 would be? 40. Done. So angle 1, if you want to just mark it in the diagram, that one would be 40. Alright, what would angle 2 be? 140. What would angle 3 be? 40. And you can go right around and get all the angles in the figure. Okay, can anybody tell me, and feel free to grab your calculator if you want to for this. What, if this angle is 110, what would angle 1 be? Anybody know? 70, definitely. What would angle 3 be? 70. What about 2? 110. That's it. That's all there is to it. Consecutive angles are going to be supplementary. All right, now I'm adding, this is a little bit weird here. So let me add, this is what we call a diagonal. And that connects to non-consecutive vertices. But the top and bottom of that figure are parallel. The left and right are parallel. Let me have you guys, here I'm going to draw this on here. Think about the top line and the bottom line are parallel. There's my transversal. I'm going to make an argument here for you. Those are parallel lines. Can anybody tell me which other angle in this diagram would be 22? Angle 3. Do you remember why? Do what? Yes, for sure. Okay, so you also, if you got these parallel lines, you got alternate interior angles. I don't have anything like that in those first two diagrams because we don't have alternate interior angles, but if I draw that diagonal in, alternate interior angles are on opposite sides of your transversal, so this would be like the transversal here. So, angle 3 is 22. Somebody tell me what other angle in that diagram is 45. Angle 2, for sure. This one is 45. That's a different set of alternate interior angles. Actually, for that one, I would have to be using, for angle 2 and the 45, you'd have to use the left side and the right side and that same thing is your transversal. So they're between those two parallel lines. They form, like that angle 2 is formed by the parallel line transversal, the angle 45, that transversal, and that parallel line. You can make that same argument. I just made that look really bad, but you can make that same argument for the other two. Anybody know what angle 1 would be? 113 has to be. And there's a bunch of different properties you could use here. That diagonal splits that parallelogram into two triangles, so you could actually use the fact that the triangle angles have to add up to 180. We're going to talk about this actually today, but the opposite angles, the angles across from each other in a parallelogram, are always going to be the same measure. Is anybody having a question? Okay. Now, the actual technical definition of a parallelogram, there's really just one requirement, and that's both pairs of opposite sides are going to be parallel to each other. I'm just going to kind of abbreviate that with a little parallel symbol. So that's technically the only requirement to be a parallelogram.
Wouldn't like squares, rectangles be parallelograms?
Yes, they are. There, we talked about that a little bit yesterday. We're just going to focus on a basic parallelogram today, but all these properties I'm going to give you today, they would apply to a rectangle, and they would also apply to a square. They would also apply to a rhombus, if you guys remember that little diagram from yesterday. So that's really, though, the only technical requirement to be a parallelogram is like basically top and bottom, left and right, parallel to each other. Okay, so I call this, just if you want to use any of these abbreviations, I call this OSP for opposite sides parallel. And I'll start to write these, that's the actual definition. I will start to write these on the board so you guys can have a visual for what these mean. Now, diagonal, I know we just mentioned that in the lovely diagram above, but this is a segment that connects two and what we call non-consecutive. So basically like not next to each other, non-consecutive vertices. It's a segment that connects two non-consecutive, so like not next to each other, vertices. They have to be across from each other to get your diagonal. All right, now I'm going to use that information to help us prove this first theorem. So whenever you have a theorem is not like a definition. A theorem is something that you have to prove. But we're just going to do these proofs in the notes. Once we prove it, you can use this property. So the first one we're going to talk about, call it OSC. It says if a figure is a parallelogram, then opposite sides are congruent. And I'm just going to use the symbol for congruent there. And let me draw you a tiny picture for what this would mean. This is, and we're going to prove this, and then you guys, that looks really bad. Pretend that's a parallelogram. Okay, opposite sides are congruent. So like the top and the bottom would be the same length, the left and the right would be the same length. That's what that property would be. I'm going to prove it to you real quick here. This can always work, and I'm going to use this little diagram to help us do it. So it says this is a parallelogram. So automatically, if you have a parallelogram, I'm going to draw these little arrows. These are not congruent symbols. Little arrows tell you that the sides are parallel to each other. So the top and bottom are parallel, left and right are parallel. So in the proof, it says to us right in the directions, ABCD is a parallelogram. We're going to prove that the opposite sides are congruent. That's the AB and the CD, BC, DA. But just given to us that this is a parallelogram is the very first step. Okay, now to help do this proof, you actually could do this two different ways. We could use either diagonal, but the one I'm going to ask you to draw, just connect the vertices here between A and C. So I'm just going to draw just the best I can, draw the diagonal in there. It would just be a segment that would connect A to C. You could do this same argument from B to D, but we're just going to focus on this one because I just need to prove it for one. All right, now, this says angle BAC, so B, middle letter is your vertex, so BAC would be this angle right here. is congruent to angle ACD, which would be this angle right here. How do I know that's true? Exactly. These are alternate interior angles. All right, so I'm just going to write alternate interior angles. Okay, now, the next little step says angle BCA. So this would go BCA would be this angle right here. And then it says CAD. So here's C, here's A is in the middle, D, this angle right here. How do I know those two angles are congruent? How could I defend that? Yeah, same thing, alternate interior angles. All right, now, see if you guys remember this from doing a proof. How do I know the segment that we drew that diagonal? How do I know AC is congruent to itself? Yes, you guys are, oh yes, good, we remember this. Okay, this is the reflexive property. Okay, now, here's what I'm gonna do. I might take this and separate it here real quick, but I basically, when I drew that diagonal in there, created two triangles. Let me just draw one to the side without the parallel lines on it. So I've got an angle here, and for the other piece, I'm trying to redraw this just so it's separated a little bit so you guys can see this. So I have a single curve, double curve on my diagram. Can you tell me why those two triangles are congruent? Do you guys remember doing like side, side angle, side, that kind of stuff? Why are these two triangles, which one of those makes these? Yes, okay, if you touch them in order, like this angle, side in between angle, angle, side angle, angle, side angle, you have to touch them in order. So angle, side angle forces those to be two congruent triangles. Okay, now, this is another thing. I don't know if you guys are going to remember. If I prove that these triangles are congruent, then the AB would be right here, and the CD would be right here. After I prove the triangle's congruent, does anybody remember how you know that all their other parts were then congruent? You remember doing that? Yes. Okay, it's called corresponding parts of congruent triangles are congruent. CPCTC. Every other letter is the C. I'm going to abbreviate that. But if I show those triangles are congruent, it forces those corresponding sides to be congruent. So the left side and the right side. And then same argument, I'm going to go 1, 2, 3, 1, 2, 3. The top and the bottom, that's B, C, and DA, sorry. Corresponding parts, congruent triangles are congruent. You could make that proof for any parallelogram. So now you will always know that if you have a parallelogram, this also applies to squares, rectangles, and any rhombus, opposite sides are going to be congruent. So we can use that in some problems. All right, the other property I'm going to walk you through real quick. And again, you guys don't have to do any proofs on the homework or anything like that. We're just going to do them in the notes together. But the other theorem here, I call this OAC, and you kind of saw this, I think, a little bit, but I'm going to prove to you why it works here. It says if a figure is a parallelogram, then what that stands for is opposite angles are congruent. Opposite angles are congruent. Now, if you have a parallelogram, you have two sets of those. So I'm just going to draw like a little tiny picture for this. So opposite angles would be like this angle and this angle would be congruent. And I'm going to draw the same exact, well no I'm not, I'm going to try to draw another parallelogram like this set. So you get two sets. The opposite angles are congruent in a parallelogram. And I'm going to prove to you real quick with a little bit different type of proof. We just did a two-column proof. This guy's called a flow proof, if you guys remember doing these. Now, I'm going to prove this for both sides, and so I have the same diagram copied twice. We're going to prove the opposite angles are congruent here. So it says given parallelogram MNPQ. So I just copied it twice. All right, so our first step is that we're just given this, and I copied that diagram twice. What I want you to do for me, just as a favor here real quick, on this one, draw the diagonal between M and P, and then on the other one, I'm going to draw the other diagonal, so I can prove both of these opposite sets of angles are congruent. All right, now, I'm going to mark this in the diagram kind of as I go. It says MN and PQ. So MN here and PQ are congruent. I'll just mark that on both. And then I also have MQ, that's the bottom, is congruent to NP. Now, my defense of that is literally what we just proved. We know if we have a parallelogram, we just proved this, that opposite sides are congruent. So I'm just using the theorem we literally just did. All right, now, we already just did this. I had you guys do this. This one says connect NQ. This one says connect MP. We don't have to defend that. We're just going to draw that in the picture. All right, let's see if I can get this all on the screen at once. All right, now, in this diagram, they're going to say NQ is congruent to itself, so reflexive. And same argument, but other diagonal on this side, 1, 2, 3. The MP is congruent to itself, so that would also be your reflexive property. All right, now, on this side, it says this triangle is congruent to the triangle I did not color just there. How could I defend that? Does anybody know what you would use for that one? Like how, yes, you have all three sides because the reflexive property and that opposite side's congruent. This is going to be side, side, side. All right, same argument here on this one, just it's a different triangle, but it's still side, side, side. We just drew the diagonal in a different location, but it's literally the same thing. This is side, side, side. And then because of that, what I'm going to get, my opposite angles. So what is this? NMQ. In this triangle, they're talking about this angle and this angle. And that's just your corresponding parts of congruent triangles have to be congruent. Those angles will correspond to each other. Same argument, but different picture over here. This angle and this angle is what they're talking about. So again, corresponding parts, congruent triangles, congruent. And then we have this theorem we can work with as well. Now that we've proved it, you could prove this for any parallelogram. You just saw the proof right there. It's not too bad to do. But those are going to have to be congruent to each other. So we're going to actually see this is what you guys are going to do in the homework. We're going to apply these theorems. So either opposite sides congruent or opposite angles congruent, depends on the picture they give you. So here's the parallelogram. These are labeling angles. So I'm going to use that I know the opposite angles are congruent. We just proved that. So how would you set up something to figure out the value of y? Like what would you do? Go ahead. Perfect. 6y plus 4 equals 3y plus 37. Okay. I'm going to grab my calculator here real quick. Who could tell me, like, how would you go about solving that equation? What would you do first? Tell me a step. What would you do? Perfect. Minus 3y. Let's keep our variable positive. All right, 6y's minus 3y is going to give us 3y's. I still have the plus 4, and then on the other side I have the 37. What do you guys want to do next? Minus 4. Good deal. All right, sorry, I'm writing too big. All right, so I've got 3y equals 33. We're going to then do what? What's your y going to be? 11. Sweet. All right, now, once we have that, if you have to go back, a lot of the questions will ask you to find the angle measures. So I'm just going to grab my calculator here real quick. Okay, so I can just plug this in. Plug it right back in. Plug it in like a Glade air freshener. All right, 6 times y is 11 plus 4. I'm just doing this right on the calculator real quick. So angle F would be 70. What other angle is also 70? Exactly. Okay, now, can anybody tell me what would the measure of angle E or angle G be? 110. Exactly right. Because these have to add up to 180, because those are consecutive angles, like that first thing we talked about today. Perfect. Is anybody having a question? Okay, now, this one, there's no degree marks of any kind, so we're not talking about any angles here. It says this is a parallelogram, find values of x and y. So automatically, this one I'm going to use that we know that the opposite sides are congruent because that's what we've got marked here. So the top and the bottom, those are going to be congruent to each other. The left and the right, those are going to be congruent to each other. So we're supposed to find x and y here. What could I set up here to start solving? Like let's say we wanted to get y. What would you set up to find y? Perfect. Y plus 3, 2y minus 8. All right, what do you want to do first to solve that? Minus y. Awesome. All right, so we got 3 equals y minus 8. Then all we got to do is add 8, right? All right, so, oh, weird. Y is also 11 in this question. Okay, now, in terms of this, we're not adding up to 180 or anything like that. So if you want to find the length of the side, I can plug the y back in. So if y is 11, let's see, these two sides, these are the sides though, those should both be 14. That's not going to tell me anything about x in that situation. With the angles, you can work with information about adding up to 180, but if we're just doing the sides, I have to do a separate little problem to find x. So to find x, I'm going to set the top and bottom. So I got the 3x plus 12 has to be equal to 5x minus 14. Sorry, I didn't leave us much space here. Okay, let me subtract the 3x. I'm just going to try and write real small. So I get 12 equals 2x minus 14. I'm going to add the 14. And so, sorry, I'm going to just go into this next question a little bit. I get 26 equals 2x. And so, anybody know what x would be? 13, exactly right. And then if I wanted to find out like the lengths of the sides, we just plug it back in. You can plug it into the top or the bottom. It should give you the same answer if we did it right. So if I did 3 times 13 plus 12, this is horribly not drawn to scale if this is the case. And then if I did, same thing, if I did 5 times 13 minus 14, it should give me the same thing. So they're both 51. Forgive, because that is way distorted in this diagram. But both of these sides would still be the same. They're both 51. Is anybody having a question? Okay, the last one is actually kind of quick. The issue with this one is can you really figure out which angle they're talking about here? So I have a parallelogram. Both diagonals are actually drawn in here, so this is a little bit more complicated diagram. So this says measure of angle BCE. So let me just, I'm going to come in here and kind of highlight this. Here's B, here's C, here's E. So I'm talking about this angle right here. It says this is 62. All right, now it says angle DCE. Let me grab a different color. So DCE would be this angle here. Is going to be 45. And the question is find the measure of angle DAB. Now DAB is this entire angle here. Anybody know how you could figure that out? Say that again?
Add both the angles together.
Exactly. Yeah, you got alternate interior angles here if you've got this. So like on this side of the diagonal, this would be 45. This would be 62, so you just literally add those two together and that should be the measure. Opposite angles are going to be congruent there, so you're just doing 62 plus 45, which should be 107. Is anybody having a question? Bless you. Okay, so homework, bless you.